Okay, we're going to start to look at the effect of air resistance or drag on the projectiles that are being fired. So just bear in mind that the drag or air resistance is always going to act in the opposite direction to the velocity. That's the key thing to remember. So if the velocity changes obviously in a projectile, the direction of the overall drag is going to change, so that's always in the perfectly opposite direction. Now you can actually break that up into two components there, whereas if you look at these here, the velocity is going up at an angle here, we'd expect the drag to be opposite to that. So there would be a drag component in the vertical direction, which is opposite to the vertical velocity, and there's a drag component going backwards in the horizontal direction, which is opposite to the forward horizontal velocity of the object. So that's going to have some effect on both the time in the air and the range and the angle it comes down at. So just some things to keep in mind. Now factors that affect how much drag you're going to get there for an object particularly would be the factors that affect the drag would be the area of cross-section of the object. If it's got a larger area of cross-section, it would have a larger drag. Whether it's got a surface texture that's rougher rather than smoother would actually affect the drag and make it larger. And obviously the shape overall would affect how much the air catches or interacts with the object as well as it goes through the air at a speed. So they talk about being streamlined and so on. And there's a drag coefficient that's sort of based on that plus the surface texture. You could also worry about the speed. Obviously it gets faster, the drag gets bigger as well, but in terms of the factors that affect the object and its drag, it depends on those three. And you can see this from a PowerPoint here. There is actually a formula that's not really in the course there. Half rho is the density of the air. This is the area of cross-section, speed squared, and D here they must have as the drag coefficient. That's often written as a C though. So in these cases here, the object has a similar area of cross-section in all these cases here. If you look at that circle, that's its biggest area of cross-section facing downwards as it moves downwards through the air. If you change that size of that area of cross-section, you get a larger drag, so it's a bigger area of cross-section. And as I said, the surface texture being rougher and the streamliness of the object. What effect will drag have on the time then? Well, if you can picture that the drag is going this way and it has got a drag component that's this way in the vertical direction, so you've got a force of drag acting down, what will that do to the time it takes to get to the top? Well, if you think about it now, you've got a drag component of force which is acting downwards in addition to the force of gravity acting downwards. So the overall force going downwards as a total is now bigger. And that's going to cause the vertical velocity component here, which is there, to reduce to zero much faster than normal. So because it reduces to zero much faster than normal, it'll take less time, and so it takes less time to get to the top. And naturally then if it doesn't go as high, it's not going to take as long overall to travel along the journey. So that's the first one. I should point out here that from that particular height down, it would take less time than normal from that height, but don't forget it's only going to get to this height here now. And so from that height there down, yes, it would take less time from there to there than normal because the drag force is going to sort of support it now because it's going to go in the opposite direction and it kind of holds it in the air. But the overall time will still go down because of that significant drop in the first time and also the drop in the height that it gets to. So that's the first one there. So if you want to look at that as a summary there. So the effect of drag here, it will lower the peak height and you will get a steeper descent angle, we'll discuss that in a minute, and we'll get a much shorter range. And the reason for that at the time of flight is, key points, the vertical velocity has a drag force going downwards as well as the force of gravity. This causes a greater vertical acceleration than normal, okay? And so the vertical velocity stops in a shorter time or drops to zero in a shorter time, and that'll give you also less peak height there. Okay, and as I've said here, on the way down from there, the drag force starts to go up against gravity, and the overall down force is lower than the normal gravity now. And that'll give you less acceleration and a slightly longer time from that height to go down than normal. But don't forget it's coming from a lower height, so overall you get a lower time there. So what's it going to do to the range then based on that? Then if you look at the range here, so this is the time is going to go down. The range is basically horizontal velocity times by time. Like that. And don't forget we already have a reduced time, so naturally the range is going to go down. But you've got another problem as well. If you look at that sort of motion there all the way through, along the whole motion there's always a horizontal velocity component, and ordinarily that would stay constant all the way through the trip, even on the way down, when it's coming back down again. But what's going to happen here is there's always going to be a drag force then in the opposite direction, a component of this one here, going backwards against it. So the drag force component is always acting against the horizontal velocity through the whole trip, and that means that this horizontal velocity is going to get smaller and smaller all the way along. So it doesn't actually stay as it is now, it actually gets shorter and shorter as it goes on the trip. And so if that horizontal velocity is going down, and the time of the year is going down, you get a huge drop in the range. You can sort of see here, I've given you some indication, but it'd actually go more than that, in fact. Okay, so the range will be lower. And then you'll be putting out key things like this product is the range, and both of these factors are going to go down. And you can explain the reason behind that. The range is the horizontal velocity times by the time. That's the key thing to get in mind. If you can point out that there's always a component of the drag force acting opposite to the horizontal velocity, you're going to reduce that velocity all the way through the trip. So that's going to cause the range to be less. But in addition to that, you're also going to get the time getting lower because it doesn't go as high as explained before. So if you look at the PowerPoint on these things, you've got a much changed trajectory here based on the time of flight being lower and shorter and giving you a lower peak, and the range being much shorter because of that product of horizontal velocity and times getting down. Now, if you look below that, they probably won't ask you this in the exam, not the stage 2 one, but the angle of impact is going to be steeper. And the reason for that is you've got a much lower horizontal velocity component now. It's actually become smaller. So it's going to come down at a steeper angle than what you would normally get if it was in a vacuum, or if air resistance was negligible or drag was negligible. One thing I've probably missed here is to talk about the shape a bit more. So if the object's got the same sort of area cross-section and it's travelling to the left here, and you look at the ones with like square corners there versus round objects versus objects that might be jagged, okay? Anything that sort of has a sharp point to it will catch the air particles more as it goes past them and cause more interaction and cause more force pulling back on the object there. So these might have all the same area of cross-section, but the amount of drag they get would actually change depending on how streamlined they are and how smoothly the air particles can get round behind them and get back in behind there without too much turbulence, I guess. So these might have the same area of cross-section, but shape is important in terms of the streamliness of that. And in your textbook, you'll actually find a picture there that shows you in order from left to right which shapes are the best and which are the worst. So it's worth looking at. Okay, thanks.